let's look at lithium versus fluorine. Lithium has 2 energy levels, right? What about fluorine? How many energy levels does it have? It only has two energy levels as well. This is 2,1 and this is 2,7, right? Okay. So we have 2 electrons here. We have 2 electrons here. This one has 1 electron and this one has 7 electrons. Now what else has changed between lithium and fluorine? Well, lithium has 3 protons here. Fluorine has 9 protons. Now, let's look at it. This energy level, they're supposed to be in the same place. I'm going to try to make sure they're exactly the same place. Close enough, right? These 2 are in the same place, right? Electrons are being pulled toward the nucleus because this is positive and this is negative, right? But this only has 3 things, and this one has 9 things, pulling on the same general area. It's kind of like saying, I'm going to take 3 people and I'm going to go move that pickup truck, versus I'm going to take 9 people and I'm going to go move that pickup truck. Who's going to be able to move that pickup truck? The 9 people. And what's going to happen is this energy level is going to come in a little bit closer to the nucleus. Okay? Because you have more force to pull it down closer. Because you have more protons there. Okay? Does that make sense? A little bit? So, what are the trends? Things get bigger as you go down because you have more energy level. And they get smaller as you go across because you have more protons to pull those electrons closer. Same energy level, but more protons pulling on that energy level to bring it in closer.
It gets smaller as you go to the right?
Gets smaller as you go to the right. So if you see, look up here, here we have lithium versus fluorine, or even look down here, rubidium versus xenon or something. The general trend is you get smaller going to the right and bigger going down. Okay? So if I look at the periodic table and I ask you, which element's larger? Arsenic or antimony? Who's bigger, arsenic or antimony? Why antimony? Antimony's down 1 row, right? Arsenic is in row number 4, antimony's in row 5. So it's up an energy level, it's bigger radius. All right, well, who's bigger, arsenic or selenium? Arsenic now, because selenium is to the right. Okay, see the difference? Now, another term that we could talk about that relates to this size is called ionization energy. Ionization energy is how much energy does it take for me to rip an electron off of an atom? That's kind of like saying, one of the things that I will talk about a lot is that electrons are like children, right? Remember we talked about them being jacked up on sugar? Well, now you have some kids and I'm going to kidnap one of your kids. The mom just looked at me like, yeah, like hell you want. Well, think about it. If you're francium You got 87 kids. You'd probably be happy for one of them to go away, wouldn't you? And the fact of the matter is, for Francium, that 87th kid, he's across town hanging out with his buddies all the time anyway. You don't ever see him. If somebody stole him, you might not know it for a while, would you? So for francium, it's really easy to take an electron because electrons are so far away. For lithium, it's only got 2 shells. It's not quite as hard. Or it's much harder, right? Electrons are closer to home. Now what about as you go across the periodic table? As I go from lithium to fluorine, what did we say happens to atomics? They get closer to the nucleus, so what do you think about?
It's harder to pull them apart.
Harder to pull them apart, wouldn't it?
Yeah.
Very good. Everybody hear that? So as I go from lithium to fluorine, the atomic radius gets smaller, it's harder to take them away. The closer to the nucleus they are, the harder it is to take them away. Does that make sense?
Makes perfect sense.
And so that's why this chart looks a lot like the last one, right? Except before we had radius decreases, now it means ionization energy increases because the electrons are closer to the nucleus, harder to take them away. Down here, atomic radius gets bigger, ionization energy decreases. Heck, francium doesn't even know where those kids are. It's like, whatever, I got 86 others, I'm good. Sure you don't want some more? Little old lithium out here's like, I only got 3 kids. You ain't taking one of mine. Right? I know where every one of them is. Poor hydrogen. Only got 1 kid. That poor kid ain't going nowhere, Jack. So, that relates to the metallic character. Metallic character is, how much do you act like a metal? Who do you think the most metal acting thing is on a periodic table is? After what we just talked about. We know where the metals are and the non-metals, right? Who acts the most like a metal? Anybody guess? Where are the metals at on a periodic table? On the left-hand side, right? So who's the most metallic?
Yeah.
Do what? The ones on the left? And who is the most metallic element of all? Who's the furthest left? The alkali metals, right? And who do you think out of that group would be the most metallic? It's either got to be at the top, lithium, or at the bottom, francium. Francium. Why do you think francium is the most metallic? Because it gives up that electron the easiest. When you give up electrons, that makes you metal. Metals give up electrons. Francium is like, sorry, love you, honey, but that kid's got to go. Can't feed all of them. Okay? Francium is the most metallic. Now, if we exclude the noble gases, who do you think the least metallic would be? The halogens. And who in particular is the least metal-like? It's either got to be the top or the bottom.
Fluorine.
You think it's fluorine? Why fluorine? Because it's got the smallest size, the highest ionization energy. It's not giving up an electron. It doesn't act at all like a metal. It is taking electrons. Not giving up kids, it's taking kids in. Okay? See the difference? So, metallic character increases as you go down, just like atomic radius did, and it decreases as you go across, just like atomic radius did. The least metallic element is fluorine. We're going to exclude the noble gases. Now, This table just summarizes all that stuff. I'm not gonna read it to you. It's in the book as a summary. I'm gonna change this slide because I don't like this. Who's the largest atom over here? Come on, choose. Help me out.
Carbon.
Carbon. Why carbon?
That's the least amount of protons pulling in the electrons.
They're all in the same row, right? They're all in row 2, period 2. And carbon's the furthest left. It has the least number of protons pulling on those electrons. Okay? So it is the largest. Things get smaller as you go across, right? Who has the highest ionization energy?
Fluorine.
Why fluorine? Because it is the smallest, right? It's holding on to those electrons. Who's in group 5A?
Nitrogen.
Nitrogen is at 5A, right? Chapter 4. Start on chapter 6. Chapter 5. Chapter 10. What if we just do the chapters like in random order? That'd be kind of cool, right?
No. I had one you said.
That'd be crazy. Because you see how we're going to use what we learned today when we do chapter 6, I promise. See you guys see some of you tomorrow. Who's in lab with me tomorrow? Allison. Yeah, okay. See some of you tomorrow.
Is there no pre-med in that one? I go home.
Yes, there
Did
is.
you see a pre-med in there?
There's pre-lab in that
I tried
one.
to find it today.
There's some pre-lab questions.
All right. Might have been stuck together.